So what does the book do that's confusing? Let's show you. Well, this is out of the book. And these are showing pipes which are open-ended. And the lines that they have representing what's going on in those pipes, your book uses pressure variation. So these are pressure graphs. They're not displacement graphs. And what they're showing for an open pipe, a pipe that's open on both ends, is that the pressure stays the same at the opening of the pipes, which happens to be true, but I don't find that particularly helpful because the way that these pipes make sound is by making the air move at the openings of the pipes. The air inside is banging on the air outside and sending waves of pressure that we hear. So I find these graphs to be kind of confusing. But yeah, in the book, these graphs are all pressure waves. They're not displacement waves. So the displacement waves are just the opposite of this. If you want to think about how the air is actually moving, you have max motion at the mouths, and you have no motion right here at the dead center in the initial condition. Okay, so we'll come back to the clipboard in a little bit when we do a little bit of math, but that will be enough to get us going for now. Okay, let's have this set up for us so it's ready when we need it. Very good. Let's go back to our smartboard slides. So this is representation of the displacement in open-ended pipes. Okay, so this is back to displacement curves, which again, I find the most intuitive, but your book chooses not to do it this way. So what we can see here, when we have an open-ended pipe, to get a resonance, we have to let the air move at the mouths of the pipes. You know what? I'm going to show what happens with closed-ended because that's the easiest. So let's go back to this here. Okay. Well, let me show you how this looks in a closed-ended pipe for displacement. Okay, so this is not the way that the book represents the transverse wave. The book will show pressure, but they also don't show closed-ended pipes. So here we go. So this is a displacement showing the displacement in a closed-ended pipe. Now, since it is closed-ended, that means that the air at the ends cannot move. It's fixed in position. So there's going to be no displacement at the end of these pipes. And to get a standing wave, we have to have it set up so there's nodes at the end. Now, there's even a simpler form than this, which I probably should show first. Okay, and that's going to be a node at the end and an antinode at the middle, like this. Okay, so this is the fundamental. This is the fundamental. When you're making sound waves, standing waves in air in pipes, this is the fundamental frequency. It's the one that will make the loudest tone, the dominant tone among all the tones that the pipe is going to be producing. You have, and again, you have a half a wavelength in here because this is a half a waveform. Either the air is compressed or it's rarefied. Well, yeah, it's a half of a waveform. It's a half of a waveform, which we can see when we represent it as a transverse wave. Okay, now here is m equals 2. This is the second harmonic, and the lambda is 2 halves of a wavelength, or 1 full waveform. We have a compression and a rarefication, and then a rarefication and a compression as the air is doing its accordion thing inside the pipe. Again, it's hard to visualize that when you think of it as a longitudinal wave, but when you represent it as a transverse wave, it's easier to see. You could have 2 lobes in here. So when you have both ends of a pipe closed, you get the same pattern that you did with springs. The possible wavelengths go by half a wavelength, full wavelength, 1.5 wavelengths, 2, and so on. And I think that you can see that if we go to open-ended pipes, which we'll do right now, that we get the same thing. Again, these are displacement curves. we're representing the displacement as transverse waves. And your primary fundamental is with both ends open. So you have maximum motion at both ends. So sound is coming out both sides of this thing. And the possible wavelengths are half a wavelength, full wavelength, 1.5 wavelengths, and so on, just like the strings, just like it was for the strings. Okay, now the thing about organ pipes is that they don't have to be open on both ends. We can have them closed at one end. Let's see, this is the one we had. Okay, so we can close off one end of the organ pipe. And when we do that, what we wind up with is a node at the closed end, because that's where the air cannot move, and an antinode at the open end. That's where the air is moving a lot. Okay, so node at the bottom of the pipe and an antinode at the mouth of the pipe. And the first time we can get that, to have that kind of resonance, node at the bottom, antinode at the mouth, is 1/4 of a wavelength. Okay, so the first resonance for an open closed pipe, closed at one end, is 1/4 of a wavelength. Then the next time it can happen is at 3/4 of a wavelength. You can see the form here. The next one is 5/4 of a wavelength. This right here, from here to here, that is one full waveform. So that's one wavelength. And then we have 1/4 more of a wave. So this is 5/4 of a wave. So the pattern here is 1/4, 3/4, 5/4, 7/4, 9/4, and so on. So it still goes up by half wavelength intervals, but it starts at 1/4 of a wavelength. Okay, so strings always go by half a wavelength, 1/2, 3/2, 5/2, and so on. Closed end pipes and open end pipes, open pipes, go by the same pattern. But organ pipes that are closed at one end and open at the other go by 1/4, 3/4, 5/4, 7/4, and so on. Now, this is significant when you're designing organs because this means that you can make a tone with a pipe that's half as long. So in this original picture that I showed here, these pipes are open at the top and closed at the bottom. And this pipe, this long pipe here, will make a certain tone. Now, you could also produce the same tone with a pipe that's open at both ends, like a piccolo or a flute. That's an instrument that's open at both ends. But to do that, you'd have to make the pipe twice as long. And if you make the pipe twice as long, it's twice as expensive, maybe more, because bigger things are harder to manufacture than small things. So organ pipes are almost always made with closed pipes that are closed at one end and open on the other. Now, by the way, incidentally, let's go back to my back to the clipboard here. You'll never see instruments that are made like this with both ends closed because the sound can't get out. It's basically a sealed can with sound inside. Now, you get really nice resonances and really nice tones in there, but you can only hear it if you're inside. So sometimes they will build buildings with acoustics that will sometimes take advantage of this or maybe neutralize it, maybe avoid it. But if you're walking down a hallway and you sing a note, you can make it resonate. Singing in the shower works really well like that because the sound can bounce off the floor and the ceiling, and you can get basically a closed end resonance and make the air in the shower resonate, or in a stairwell. But musical instruments, they're not made this way. Musical instruments are always open at least one end and sometimes both. Okay, so let's figure out how we can do some math with this, because what good is physics without math? Let's see, there we go. So what we're going to do is we're going to figure out how long an organ pipe has to be to produce a certain tone. Okay, so suppose we want to make a musical instrument. It doesn't have to be an organ, but a musical instrument that is going to have a frequency of 900 hertz. Okay, I don't know why we want that, but we want it. 900 hertz frequency, and we want to find out the shortest pipe that we can make with closed end, closed, open. So one end closed, and then the shortest with an open, open. Okay, that's what we're trying to figure out. Now, the first step of this is to figure out what the wavelength of this sound is going to be. So to figure out the wavelength, we need our wave equation, V equals lambda F. And as you may or may not recall, our textbook likes to use 343 hertz as the speed of sound. Okay, now in reality, not 334 hertz, 343 meters per second as the speed of sound. Now, in reality, the speed of sound varies. Turns out it depends on the temperature, and it varies quite a bit. But their book uses 343 as a typical speed of sound, and that's fine. That's what we'll go with. So we're going to figure out what the wavelength is for a 900 hertz sound. So we come up with 343 hertz, meters per second rather, is equal to lambda times 900 cycles per second, which is hertz. Okay, the math on this is not complicated. We are going to go with 343 divided by 900, and we come up with a wavelength. Lambda is equal to 0.3811 meters, which is equal to basically 38 centimeters. We're going to go with that. Okay. It's fine to round it off to 2, particularly in this context, because speed of sound is approximately 343, but yeah, there we are. Anyway, so we have our wavelength. Lambda is 38 centimeters. So now we have to think about what is the shortest amount of that wavelength that we can fit in a pipe and still have it resonate to make a tone. So the closed is a shape like this, open at one end, closed at the other. And as you recall, for a closed end pipe, we have to have a node at the bottom of the pipe and an antinode at the mouth of the pipe. This is 1/4 of a wavelength. So 1/4 times 38 centimeters is equal to 9.5 centimeters. That's the shortest musical instrument that we can make that will produce a 900 hertz tone. If we go shorter than that, the waveform can't fit in it. It will never resonate. It will never make that tone. Okay, now how about the open, open? So if it's open, open, we are going to have a node, or an antinode rather, at both ends. That's not very well drawn there, but hey, what are we going to do? It's freehand. There we go. That's better. Okay, so the pipe has to be have an antinode at both ends. The air has to be able to move fast at both ends of this for the sound to be able to come out and for it to be able to resonate. So this is 1/2 of a wavelength. That's the first time that this can resonate. So half of 38 centimeters would be 19 centimeters. And that would be the shortest length for an open pipe. Now, by the way, why does it resonate when it's open at both ends? The reason is because the instrument is not able to permanently change the pressure in the room. The pressure in the room is what it is. It's a huge room and the pressure is what it is. So that means that the pressure at the mouth of the pipe is not going to change. So you have to have a condition for it to be stable where the pressure at the mouth always stays the same. And that is if you do a pressure curve, is where the pressure stays constant all the time. Okay, so where the pressure stays constant, that's where you have the max motion, the max displacement, and vice versa. Where you have the minimum displacement, that's where the pressure changes the most. So when you have an open-ended pipe like this, open, the pressure at the center of the pipe is getting very compressed, very rarefied, very compressed, very rarefied. That's what's happening exactly at the center of this thing. But the pressure at the end stays the same, but that's where you get max motion. That's what shakes the air in the room the most. That's what makes the most sound. That's what makes the best instrument. Okay, that's what we've got. That should be enough to get you started on your homework. This has been a long one. I think I'll have to break it into a couple pieces. But that'll be enough to get you through the homework. And you may need a little help from the textbook itself, but I think this is enough to get you going. All right, thank you for your time. We will see you next time.